Already today, we are no longer observing isolated weather anomalies, but signs of a systemic destabilization of the planet's climate system. The volume of heat accumulated by the world's oceans, this is roughly equivalent to 37 years of total energy consumption by all of humanity. The consequences may include larger hail, more anomalous precipitation patterns, and sharper transitions between drought and torrential rainfall. Humanity has visibly observed less than 0.001% of that region. Today, the world's oceans are not merely warming rapidly. The rate of warming itself is accelerating. Micro and nanoplastic. By contaminating both the ocean and the atmosphere, interferes with processes of heat exchange, gas exchange, cloud formation, and the hydrological cycle. Nature is indifferent to how comfortable institutions may feel or how political strategies are designed. The physics of these processes continue to unfold according to their own laws, regardless of our doubts. Greetings. My name is Egon Cholakian. Today, I would like to address one of the most consequential issues in climate science, ocean warming. We will examine how the accelerating warming of the ocean is already exceeding the limits of accepted models, what processes may be unfolding in the ocean depths, and how these developments are reshaping our understanding of climate predictability. Already today, we are no longer observing isolated weather anomalies, but signs of a systemic destabilization of the planet's climate system. Let me remind you that in the very first weeks of February 2026, the World Meteorological Organization was compelled to officially state that the year had already been marked by extreme heat, cold precipitation, and wildfires. January 2026 ranked as the 5th warmest January ever recorded. At the same time, Europe experienced its coldest January since 2010. To someone unfamiliar with the physics of the climate system, this may appear to be a contradiction. In reality, however, it is one of the clearest indicators of destabilization. When the climate system moves out of equilibrium, it does not mean that temperatures simply rise uniformly everywhere. What it does mean is that the familiar mechanisms that distribute heat, moisture, and air masses begin to break down. The behavior of jet streams becomes disrupted. The polar vortex weakens and becomes distorted. Arctic cold air pushes far to the south, while warm air moves into regions where it had rarely appeared before. This is precisely why, even as the planet continues to accumulate heat overall, we begin to see not only heat waves, but also waves of extreme cold. And this is already happening. In the Northern Hemisphere, at the beginning of 2026, cold intrusions affected both Europe and North America. Europe experienced a series of storms accompanied by heavy precipitation, powerful winds, and high waves stretching from Ireland and the United Kingdom to Portugal, Spain, and across the entire Mediterranean. At the same time, the Southern Hemisphere was recording extreme heat that fueled massive wildfires in Australia, Chile, and Patagonia. In southeastern Africa, torrential rains triggered destructive flooding, particularly in Mozambique. There, the floods affected at least 600,000 people. Hundreds of thousands were displaced, and approximately 30,000 homes were destroyed or severely damaged. These natural disasters occurred in different parts of the world, but the climate system connects them through a single common process: the anomalous warming of the ocean. It is the abnormally heated ocean that increasingly transfers excess energy and moisture into the atmosphere. From the surplus of heat and moisture, storms, torrential rains, and waves of extreme heat and cold begin to form. Yet it is important to understand that the ocean does not warm or interact with the atmosphere under sterile conditions. This delicate system has already been altered by another factor of anthropogenic origin, micro and nanoplastic. By contaminating both the ocean and the atmosphere, interferes with processes of heat exchange, gas exchange, cloud formation, and the hydrological cycle. Water vapor in the air does not condense into raindrops on its own. It requires particles around which condensation can occur, the so-called condensation nuclei. Under normal conditions, these include dust particles, sea salt, soot, and other aerosols. Today, nanoplastic is prevalent in measurable quantities both in the ocean and in the atmosphere. Modern research shows that such particles can interfere with the microphysics of clouds and precipitation. In particular, a 2024 study published in a Journal of the American Chemical Society demonstrates that atmospheric plastic can participate in cloud processes and due to its physical properties, may act as potential condensation nuclei and ice nucleating particles. In other words, micro and nanoplastic are beginning to participate directly in cloud formation and the condensation of atmospheric moisture. This in turn influences how, where, and with what intensity precipitation occurs. The consequences may include larger hail, more anomalous precipitation patterns, and sharper transitions between drought and torrential rainfall. Because the influence of charged micro and nanoplastic particles is largely absent from current models, they effectively introduce an additional noise variable into the system. As a result, they may increase the uncertainty of both short-term weather forecasts and long-term climate projections. However, the influence of plastic is not limited to the atmosphere. The ocean and the atmosphere together form a single climate system. Water possesses a unique capacity to accumulate enormous amounts of heat while gradually increasing its temperature. A 10-meter layer of ocean water can absorb more heat than the entire atmosphere of the Earth. During the day, the ocean absorbs heat, and at night it releases it back into the atmosphere, smoothing temperature fluctuations in the air and functioning as a natural climate air conditioner. In addition, the ocean removes heat from lithospheric plates and releases it back into the atmosphere. There are serious reasons to believe that the large-scale contamination of the ocean by micro and nanoplastic is beginning to disrupt this finely balanced system of thermal regulation. According to available data, nanoplastic particles concentrate in at least 3 key layers of the ocean: near the surface, on the seafloor, and in the thermocline, where water temperature and density change sharply. Plastic particles with a surface charge interact with water molecules at the level of hydrogen bonds. As a result, the physical and chemical properties of seawater begin to change. The transfer of heat to the atmosphere slows, and zones of overheating begin to form within the ocean's water column. This brings us to a fundamentally important question. Yes, according to our assessment, micro and nanoplastic does indeed exert a serious influence on the thermal regime of the world's oceans. It can disrupt heat exchange, alter water properties, interfere with gas exchange between the ocean and the atmosphere, influence cloud formation, and affect the hydrological cycle. Yet, despite the seriousness of this factor, one point must clearly be understood: micro and nanoplastic is not itself a source of heat. It merely disrupts the natural mechanism through which heat is released. And this leads us to the central question. If micro and nanoplastic does not generate heat, then what is the source of the additional heat that is now being detected in the ocean? To answer this question, allow me to turn to the given facts. Today, the world's oceans are not merely warming rapidly. The rate of warming itself is accelerating. New studies published in 2024 through 2025 show that the rise in ocean temperature can no longer be described as a steady and gradual process. The pace of warming itself is increasing. According to a 2024 study published in Nature Communications by Italian scientists, the ocean steadily accumulated increasing amounts of heat between 1961 and 2022, and the acceleration of this process was statistically significant. Another study conducted in 2025 by scientists at the University of Reading found that the ocean surface is now warming approximately 4.5 times faster than it did in the late 1980s. At that time, the rate of warming was about 0.06 degrees Celsius per decade. Today, however, it has reached approximately 0.27 degrees Celsius. Traditionally, this warming has been explained by anthropogenic greenhouse gas emissions. However, in recent years, the pace of warming has increasingly moved beyond what was expected based on existing climate models. This is precisely why it is particularly significant that scientists themselves have begun to point this out directly. It is worth recalling that throughout 2023 and the beginning of 2024, global ocean temperatures reached record levels for 450 consecutive days, an event that at the time had no precedence in the observational record. Dr. Brian McNally, a senior research associate at the University of Miami's Rosenstiel School of Marine and Atmospheric Science, described the situation in an interview with NBC News. And I quote, "It's not just an entire year of record-breaking ocean temperatures, but it's the margin it's breaking them by. It's not even close to what the previous record was." End quote. At the time, Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, stated in an interview with AFP that previously unaccounted for factors might be involved in what is occurring. Allow me to quote his words as well. And again, I quote, "The long-term trends we understand, and it's being driven by greenhouse gases. It's being driven by anthropogenic effects. But what happened in 2023 was that, and then plus something. And that plus something is much larger than we expect, or as yet can explain." End of his quote. In essence, this meant that the observed temperatures did not merely surpass previous records. They pointed to the presence of an additional heating mechanism that lies beyond the usual long-term trends described by earlier climate models. British marine geophysicist Dr. Rob Larter also offered a highly revealing comment in the New York Times. And again, I quote, "It's quite scary, partly because I'm not hearing any scientists that have a convincing explanation of why it is we got such a departure. But the impression at the moment is that things have gone further and faster than we expected." End of quote. Professor John Abraham of the University of St. Thomas also spoke candidly about this issue. Quote, "I do fear there may be something else going on that is causing a long-term change in ocean surface temperatures we hadn't predicted." End of his quote. Listen to what he said next. Quote again, "What we see now driving high temperatures is something in addition to the El Nino and can't be explained by the arguments being given 6 months ago or 12 months ago. Sea surface temperatures are higher elsewhere and very far from El Nino locations." End of his quote. This was yet another voice supporting the assumption that long-term changes in ocean temperature may be influenced by previously unknown or unaccounted for factors that are absent from existing models. Equally important is the fact that anomalous warming did not stop in 2025. Although ocean surface temperatures last year did not reach an all-time record, an international analysis published on January 9th in the journal Advances in Atmospheric Sciences showed that in 2025, the ocean accumulated more heat than in any other year in the modern observational record. In other words, the ocean surface did not set an absolute record. However, the total amount of heat absorbed by the water column over the course of the year did reach a record level. The volume of heat accumulated by the world's oceans, the so-called ocean heat content, increased by 23 zetajoules in 2025. This is roughly equivalent to 37 years of total energy consumption by all of humanity. If an additional factor is indeed operating within the climate system, one that has not been incorporated into existing models, it may well be one of the reasons why the ocean is not merely warming rapidly, but warming with acceleration. The year 2025 is especially important precisely because it allows us to see this more clearly. The ocean surface that year did not exhibit record warming, yet the amount of heat accumulated throughout the entire water column reached the highest level in the observational record. This leads us to a fundamental conclusion. In 2025, this unknown factor did not act from the surface. It is possible that its consequence may later become visible at the ocean surface. But one fact is already clear. In 2025, the ocean received a record amount of additional heat. And this is where the question becomes particularly acute. Let me repeat. If micro and nanoplastic can only retain heat by disrupting its natural dissipation, yet does not generate heat itself, then where does the additional heating of the ocean originate? To explore this question, let us descend into the depths of the ocean. Recent studies show that warming is occurring not only at the surface, but also at the ocean's deepest layers. Scientists at the National Oceanic and Atmospheric Administration, NOAA, have found that in the Argentine basin, warming below 4,500 meters deep occurred between 2009 and 2019 at approximately 0.02 degrees Celsius per decade. At first glance, this figure may seem small. However, we are not dealing with a small volume of water, but with the immense masses of the deep ocean. Raising such a mass even by fractions of a degree requires an enormous influx of energy. Moreover, at such depths, temperature variations are typically measured in thousandths of a degree, meaning the recorded change was hundreds of times larger than the usual fluctuations. A similar pattern has been observed in waters south of the polar circle. In 2020, oceanographers from the Alfred Wegener Institute, Helmholtz Center for Polar and Marine Research, found that over preceding 3 decades, the waters of the Antarctic Weddell Sea at depths greater than 2,000 meters were warming 5 times faster than the rest of the world's oceans. At the same time, according to the researchers themselves, the upper 700 meters of water showed almost no warming whatsoever. In 2018, scientists writing in the journal Oceanography emphasized that a growing consensus within the scientific community indicates that ocean warming also affects layers deeper than 2,000 meters. Particularly noteworthy is that, according to their review, at depths below 4,000 meters, the southernmost deep ocean basins are warming approximately 10 times faster than those in the north. This consensus was also reflected in the report 2013 of Intergovernmental Panel on Climate Change, IPCC, based on a range of other studies. The report acknowledged that the ocean is warming not only at the surface. The water layer between depths of 700 and 2,000 meters has been accumulating heat since at least 2003. The IPCC also noted that warming extends to much greater depths, from around 3,000 meters to nearly the ocean floor, particularly in Antarctic bottom waters. Moreover, the report stated that the highest rates of deep ocean warming globally were observed at depths of around 4,500 meters. In other words, we are effectively talking about warming occurring very close to the sea floor. At the same time, the IPCC emphasized that a deep ocean is far less studied than the surface because the available data from those depths remain extremely limited. Nevertheless, the report stressed that the warming of deep and bottom waters is part of the overall picture. The ocean is progressively absorbing excess heat into ever deeper layers, taking on more than 90% of the climate system's energy imbalance. From my perspective, the discussion should have long ago expanded beyond surface warming to include changes in the deepest layers of the ocean. This is a fundamentally important point. Solar radiation cannot serve as a sufficient explanation for the warming of deep ocean layers. Sunlight penetrates the water column only to a depth of roughly 200 meters. And even accounting for vertical mixing, the influence of surface heating can extend at most to around 700 meters. A widely accepted hypothesis suggests that surface waters are first heated by the sun and the atmosphere, after which global circulation gradually transports that heat into deeper layers. However, the results of a recent study by the Ocean University of China call this framework into serious question. The researchers identified a phenomenon they described as subsurface marine heat waves. They found that roughly 1/3 of all marine heat waves do not appear at the ocean surface at all. Another roughly half are visible at the surface only during certain stages of their development, remaining hidden within the water column during other phases. If the atmosphere were the primary source of heat, it would be reasonable to expect thermal anomalies to first appear at the surface and then propagate downward. Yet observations reveal a different pattern. A substantial portion of heat waves exist independent of surface warming. All of this points to the need to seriously consider the possibility of an additional energy source acting from below. The problem is that this part of the ocean remains least studied. Deep-sea regions are extremely difficult to access and extraordinarily expensive to investigate. In many cases, temperatures at great depths are not measured continuously, but only during infrequent research expeditions, which may occur once every several years or even once a decade. Marine biologist and oceanographer Sylvia Earle often remarks, and I quote, "We know the surface of Mars better than our own ocean floors," end quote. To this day, unfortunately, science has not established a systematic means of monitoring changes occurring directly at the ocean floor. Standard Argo floats typically operate only to depths of about 2,000 meters, whereas the average depth of the ocean is significantly greater. And the processes most relevant to our discussion may be occurring near the seafloor itself. In May 2025, researchers from the Ocean Discovery League published a paper addressing our limited knowledge of the deep ocean. The article notes that although ocean areas deeper than 200 meters cover about 66% of the planet's surface, humanity has visibly observed less than 0.001% of that region. This corresponds to an area roughly 1/10 the size of Belgium. And sadly, this implies something profoundly important. We still observe the ocean floor not as a continuously monitored system, but as an immense dark territory that is illuminated only occasionally by the beam of a flashlight. On the screen now, you can see a map showing the activity of deep-sea dives from 1958 to 2024, taken from the Article 1 mentioned earlier. The colors ranging from yellow to purple on the gray background indicate the number of deep-sea submersible dives per 250 kilometers squared, not the actual area that has been visually observed. The real area directly observed on the seafloor is far too small to be represented on a map at this scale. This means we may be missing not only individual landforms or ecosystems, but also the very energy dynamics of this vast, largely unexplored territory. So what could this hidden factor be that adds heat to the ocean from below? In oceanography, this factor has long been known. It is geothermal heat, heat that enters the ocean through the oceanic crust from the Earth's interior. The ocean floor is not merely a cold boundary. In many places, it is an active geological environment through which energy is continuously transferred into the water. It is precisely on the ocean floor, about which we still know so very little, that a vast number of geological structures remain insufficiently studied. Submarine volcanoes, tectonic faults, mid-ocean ridges, and hydrothermal vents. This represents an enormous portion of our planet itself, hidden beneath the water. In these zones of active volcanic and tectonic processes, geothermal heat flux is at its highest. Traditionally, it has been assumed that geothermal heat flux is too small compared with solar energy to significantly influence the overall warming of the ocean. For this reason, heat from the Earth's interior has often been treated as a secondary and nearly constant background factor. However, allow me to clarify something very important. Heat rising from the Earth's interior through the ocean floor plays a far more significant role in shaping deep ocean processes than has commonly been assumed. Even if, at the global level, discussions of warming must often focus on anthropogenic factors. For example, numerical modeling that includes geothermal heat flux shows that circulation of cold bottom water near Antarctica becomes approximately 33% more intense than in simulations that exclude seafloor heating. Numerical experiments also demonstrate that even a realistic and relatively weak heat input from below can raise bottom water temperatures by up to 0.4 degrees Celsius and significantly alter the thermal regime in the deepest layers of the ocean. Because warmer water has lower density, such heating reduces the stability of ocean stratification and can noticeably influence the circulation patterns of deep cold waters. And at this point, we are speaking only about calculations that use background values of geothermal heat flux, values that are typically assumed to remain constant over time. But consider this. Could that heat flux change, specifically increase, for some particular reason? For my regular viewers, the answer should be an obvious yes. When we speak about tectonic activity, magmatic processes, submarine volcanism, and hydrothermal systems, and the ascent of magma toward the surface of the oceanic crust, the total heat flux from the Earth's interior can indeed intensify. This becomes particularly relevant if we recall that the Earth is currently experiencing a period of intensified geodynamic activity, a topic I have discussed extensively in my previous addresses. During such periods of geodynamic activation, the heat flux entering the ocean from the seafloor can increase as well, and through several different mechanisms. First, the inflow of heat through the oceanic crust itself intensifies. When hotter magmatic masses move closer to its base, the transfer of heat upward increases from the Earth's interior to the bottom rocks and then to the bottom waters. In other words, the seafloor begins to function as a more heat surface through which additional thermal energy continuously enters the ocean. Second, increased internal heating is accompanied by rising seismic activity. This is not merely a chain of isolated earthquakes. It is a sign that energy and stress redistribution is intensifying deep within the Earth, that the crust and the upper mantle are entering a more mobile state. As a result, faults, mid-ocean ridge zones, regions of ocean floor deformation, and other geological structures become more active, allowing deep heat to transfer upward more readily. One example of the localized influence of seismic activity on heat release was demonstrated by an international group of scientists as early as 2004. They presented several striking cases in which sequences of underwater earthquakes were accompanied by sharp and highly localized increases in sea temperature, and even temporary changes in ocean currents. According to their observations, a swarm of earthquakes first occurred on the ocean floor at depths of about 10 kilometers, lasting several days or even weeks. Sometime later, satellite maps began to show patches of anomalously warm water above the same region. In one case in the Adriatic Sea, surface temperatures rose by more than 5 degrees Celsius. In the area of the Turkish Straits during the summer of 2003, anomalies exceeding 9 degrees Celsius were recorded. To explain such events, the authors proposed a bold hypothesis. Deep processes occurring at the boundary between the Earth's core and the mantle heat, the base of the lithosphere, intensify magnetism and hydrothermal emissions on the ocean floor, and this additional heat then reaches the surface weeks or even months later in the form of warm anomalies and shifts in ocean circulation. On this basis, they suggested that such episodes may contribute to certain extreme events, such as unusually hot summers, and possibly even play a role in broader warming trends. Subsequent studies provide further support for this idea. For example, a 2010 study demonstrated a fairly strong relationship between earthquakes and climate variability in the equatorial Pacific Ocean. Researchers examined more than 30 years of observations from 1973 to 2008, comparing two time series, seismic activity in the Pacific Ocean and fluctuations in the tropical climate, including Niño episodes. Their analysis showed that bursts of seismic activity and increases in total seismic energy released generally preceded El Niño peaks by about 1.5 years. In other words, the characteristic peaks in earthquake activity and the peaks of the warm phase in the Pacific Ocean not only correspond with one another, but were consistently offset by a fairly stable time interval. Over the 30-year observation period, the authors also found that the seismic energy released in the Pacific Ocean had, on average, roughly doubled. A similar analysis was conducted by Professor Arthur Vittorito, a doctor of geographical sciences and a specialist in physical geography and climate. He compared two indicators: the number of earthquakes with magnitudes above 4.5 occurring on the ocean floor and changes in global atmospheric temperature. According to his findings, beginning in 1995, the number of such earthquakes along the mid-ocean ridges began to increase. These ridges form a global underwater mountain system stretching approximately 60,000 kilometers, where new ocean crust is actively created. As Vittorito demonstrated, a fairly strong relationship exists between the increase in seismic activity in these zones and the rise in global temperature. The correlation coefficient exceeds 0.78. For climate data of this scale, this is considered a very high value, indicating a statistically significant and noteworthy correlation. At the same time, the rise in atmospheric temperature does not occur simultaneously. Instead, it follows the increase in seismic activity with a delay of approximately 2 years. According to the professor's hypothesis, this relationship may be explained by the fact that intensified seismic and volcanic activity along the mid-ocean ridges increases hydrothermal emissions and provides additional heating to ocean water. This extra heat is then transferred to the atmosphere with a delay of about 2 years. The third pathway through which heat is transferred from the Earth's interior is the intensification of volcanic activity, including submarine volcanism. When magma rises closer to the surface of the oceanic crust, it not only heats the surrounding rocks, but also in some places breaks through the higher levels, forming localized yet extremely energy-intensive sources of heat. This is no longer a uniform, weak background effect, but powerful pulses of thermal energy released into the ocean. It is important to understand that submarine volcanoes is not a rare exception, but one of the primary forms of volcanic activity on Earth. According to modern estimates, about 75% of all volcanic eruptions on the planet occur underwater. In many cases, the consequences of these deep-sea eruptions are not visible at the ocean surface. As a result, we observe only part of what is happening and are often unable to fully assess the true scale of submarine volcanic activity. Nevertheless, even the available observations indicate that many volcanic systems around the world are currently showing signs of increasing anomalous activity. According to data from the Smithsonian Institution, the number of days each year of which volcanic eruptions are recorded worldwide has been rising. Moreover, it is not only the frequency that has changed. Increasingly, cases are being reported in which erupted lava exhibits unusual properties. It is subheated and possesses an atypical chemical composition characteristic of magma rising from much deeper layers of the mantle. This is especially important in the context of our discussion because such magma carries greater amounts of deep internal energy. If these processes are intensifying not only on land but also in submarine volcanic zones, this would imply an additional influx of heat into the ocean from below, through the heating of surrounding rocks, the release of magma, and the overall strengthening of the thermal emissions from the ocean floor. The fourth pathway for the transfer of heat from the Earth's interior is the activation of hydrothermal systems. In essence, these are natural channels of heat exchange between the Earth's interior and the ocean. Seawater penetrates into layers of heated rock, warms up, becomes enriched with minerals, and then returns to the ocean in the form of hot hydrothermal discharges. If the internal energy of the Earth increases, such systems begin to operate more intensely, transferring greater amounts of heat into the surrounding water. The key point is simply this. During periods of geodynamic activation, the ocean receives not merely a little more heat from below. The entire system of energy transfer from the Earth's interior to the ocean becomes intensified. Both the background geothermal heat flux through the seafloor and localized releases of heat in zones of faults, volcanism, and hydrothermal activity increase. In such periods, the ocean floor becomes not merely a boundary, but a far more active source of heating. Moreover, these phases of activation can vary in scale. Relatively moderate episodes are followed by more powerful intervals during which substantially greater amounts of energy enter the planet's deep interior layers. During these stronger phases, the Earth's interior heats more intensely, magma ascent becomes more vigorous, crustal deformation grows stronger, the number and magnitude of earthquakes increase, and volcanic activity intensifies. As a consequence, even more heat is transferred into the ocean from below. In other words, we are not dealing with random fluctuations or isolated anomalies. We are dealing with a large-scale geodynamic process in which the energy within the Earth's interior increases, transforming into internal heat that is then released through the ocean floor. This means that the geothermal contribution to ocean warming in the present era should no longer be regarded merely as a negligible background factor, but rather as a component that may intensify significantly. This raises a fundamental methodological question. Although numerous scientific studies already convincingly demonstrate that geothermal energy makes a meaningful contribution to ocean warming, this component is still largely absent from most existing models of ocean heating and climate calculations. Is it not time to reconsider this aspect and at least begin systematically testing scenarios in which variable geothermal flux is included as a separate amplifying factor? Anomalous ocean warming is no trivial matter. It directly intensifies flooding, extreme precipitation, hail, storms, powerful winds, and hurricanes. If the ocean is warming not only from above, but also from below, due to an additional influx of deep heat, then ignoring this mechanism is no longer scientific caution. It becomes a dangerous form of blindness. Are we truly prepared to wait until the ocean warms to the point where familiar extreme events begin to shift into entirely new class of intensity, megatornadoes, megastorms, and megahurricanes? Please, let me repeat myself. Ocean warming is not occurring linearly. It is accelerating. Against this backdrop, it is genuinely striking how readily we continue to rely on models that have already been lagging behind observed reality for several consecutive years. One begins to wonder whether their predictive value has quietly been abandoned, rather than openly acknowledging that it may be time to revise the models themselves. And here I must once again return to the issue of micro and nanoplastic. For millions of years, the Earth possessed a powerful system of self-regulation, a kind of natural planetary immune system. One of its central components were the world's oceans, which functioned as a planetary thermoregulator, absorbing, redistributing, and dissipating excess heat, including heat rising from the Earth's interior. It was precisely this mechanism that helped the planet pass through periods of geodynamic activation. But we have begun to break this mechanism. One of the most dangerous factors is the large-scale contamination of the ocean with micro and nanoplastic. We are no longer speaking merely about debris floating in the water. We are speaking about the substance that interferes with the very physics of oceanic heat exchange. The consequences of disrupting the finely tuned mechanisms of heat transfer through micro and nanoplastic are far more serious than is commonly assumed. The ocean is not merely warming. It is now less capable of releasing heat, including the heat that would normally escape from the Earth's interior during periods of geodynamic activity. This means that lithospheric plates cool less efficiently, while part of the deep internal heat begins to accumulate within the system. This represents a profound interference with the planet's thermoregulation mechanism, creating the risk that the current period of geodynamic activity could become stronger than any previously observed on Earth. As a result, we are facing a new type of combined crisis. The source of additional heat lies in the intensifying geodynamic activity of the Earth, while micro and nanoplastics simultaneously blocks the natural mechanisms that dissipate this heat and disrupts atmospheric processes. Humanity is not yet prepared for such a crisis. Today, the window of opportunity for action is no longer measured in decades. It is measured merely in years. And I say this not as a rhetorical figure, but based on the speed of the changes we are already observing. The accelerating warming of the ocean, the deepening of weather anomalies, the intensification of seismic and volcanic instability, and the continuing exponential accumulation of micro and nanoplastic in the hydrosphere and the atmosphere. Against an existing backdrop of how rapidly the ocean itself is changing, continuing to address these issues at the pace of endless negotiations carries serious risk. It is difficult to justify another 10 or 20 years spent debating whether new factors are convenient to acknowledge or whether they fit neatly into existing models. Nature is indifferent to how comfortable institutions may feel or how political strategies are designed. The physics of these processes continue to unfold according to their own laws, regardless of our doubts. I invite you to reflect seriously on this, because life is worth fighting for.